Scientists unveiled the dark matter of electronics, a breakthrough in quantum information research. Using one of the world's most advanced spectroscopy systems, researchers have made the first direct observations of dark excitons, elusive quantum quasiparticles inside atomically thin materials. This achievement, led by scientists at the Okinawa Institute of Science and Technology, OIST, could reshape the future of both classical and quantum information technologies. Their findings, published in Nature Communications, establish a framework for controlling and exploiting these long-lived quantum states for next-generation computing. Why dark excitons matter? In conventional electronics, information is processed by manipulating the charge of electrons. In emerging fields such as spintronics, researchers use electron spin as the information carrier. More recently, valatronics has explored a third dimension, encoding information in the distinct momentum states, or valleys, that electrons occupy within a crystal's electronic structure. Dark excitons take this one step further. Unlike ordinary, light-emitting bright excitons, dark excitons are quantum states in which the electron and hole do not match in either spin or momentum. Because they do not readily emit light, they are less prone to environmental disturbances, such as stray photons or thermal noise. This makes them highly stable quantum information carriers, potentially superior to today's qubits, which are extremely sensitive and require ultra-cold temperatures to maintain coherence. Dark excitons have great potential as information carriers because they naturally avoid interactions with light, preserving their quantum states for longer, explains Professor Keshav Dani, head of OIST femtosecond spectroscopy unit. But this very invisibility makes them difficult to create, observe, and control. Our work provides a direct way to do all three. Bright versus dark excitons, mapping the energy landscape. Over the last decade, atomically thin semiconductors known as transition metal dichalcogenides, or TMDs, have attracted enormous interest. When TMDs absorb light, electrons are excited from the valence band to the conduction band, leaving behind positively charged holes. These electrons and holes form excitons, bound together by electrostatic forces. Bright excitons occur when the spin and momentum of the electron and hole align. They recombine within a trillionth of a second, picosecond, emitting light. Dark excitons emerge when there's a mismatch in either momentum or spin. Spin-dark excitons occur when their spins differ within the same valley. Because these mismatched states cannot recombine immediately, dark excitons persist for nanoseconds, orders of magnitude longer than bright excitons. This extended lifetime, combined with reduced environmental interaction, makes them particularly appealing for robust quantum information storage. The mismatch prevents immediate recombination, allowing dark excitons to survive much longer, notes Dr. David Bacon, co-first author, now at University College London. This isolation from the environment is exactly what we need for stable information carriers. Pioneering dark valatronics. The unique symmetry of TMD crystals enables valley-selective excitation. Using circularly polarized light, researchers can create bright excitons in a specific valley. These excitons rapidly scatter into dark exciton states, potentially preserving valley information far longer. Identifying which dark exciton species retain this information is key for developing dark valatronics, a new branch of quantum information science. Understanding how valley information survives inside dark excitons is essential, explains Dr. Vivek Parekh, co-first author and now a presidential postdoctoral fellow at Caltech. This is a decisive step toward practical valatronic applications. Tracking quantum dynamics on the femtosecond scale. To observe these fleeting states, the OIST team used their time and angle resolved photoemission spectroscopy (TRAPS) setup, one of the most sophisticated in the world. Equipped with a compact extreme ultraviolet light source, the system can simultaneously capture momentum, spin, and population dynamics of electrons and holes in real time, something never achieved before. Their measurements revealed a two-step transformation. Within a picosecond, some bright excitons are scattered into different valleys by phonons or vibrations in the crystal lattice, becoming dark momentum. Subsequently, spin-dark excitons dominate, persisting on nanosecond timescales and maintaining valley information. This unprecedented temporal and momentum resolution allowed the researchers to map the complete evolution of excitons from bright to dark states. With TRAPS, we've directly visualized which dark excitons preserve valley information and for how long, says Dr. Julian Madeo of OIST. This lays the foundation for a new era of dark valletronics and future quantum technologies. Scientific significance and future outlook. This study resolves one of the central challenges in valletronics and exciton physics: how to access, track, and control dark excitons, which are invisible to conventional optical probes. By providing a quantitative recipe for observing and manipulating these states, the work opens up exciting directions in quantum information processing with more robust, thermally stable qubits, low-power classical electronics exploiting exciton dynamics instead of electron charge, and fundamental quantum physics revealing how light, lattice vibrations, and quantum states interact in ultra-thin materials. In short, they have not only detected the dark matter of electronics, they have provided the tools to harness it.